Welcome to Module 5. In this module, we will talk about correlation. So, throughout this module, we will talk about different types of correlation analysis, and we will also cover a little bit about assumptions before doing correlation analysis. And we will see how to interpret the results, and we will see at the end how to perform correlation analysis using SPSS. This module covers Chapter 8 from your textbook. There are a couple of different ways in order to measure relationships among variables. So we can use scatter plots, which is kind of a graph, and we can see if there is any relationship between two variables. We can use covariance, and we can use Pearson's correlation coefficient. Remember, there are more than these methods to measure relationships, but these are the main ones. And depending on the type of data we have, we can choose different methods to measure relationships, and we will talk about that later. So, for example, if our data it's normally distributed, and it met, let's say, it meets the assumptions of normality and other assumptions, which we will talk about that. We will use Pearson's correlation coefficient. That's going to be our parametric procedure or parametric analysis. Let's say our data, our variable is not continuous variable. It is ordinal, or it is nominal, or it is not normally distributed. The normality assumption didn't meet there for our variable. Then we can choose non-parametric tests, which we saw in previous module. So in the non-parametric test for correlation analysis or for measuring relationships, we can switch over to other tests. We can use Spearman's rho or Kendall's tau. These are non-parametric versions of Pearson's correlation, which is a parametric procedure. So remember, the Pearson's correlation, it's our parametric analysis. Spearman, Kendall's tau, these are our non-parametric measures. So whenever our assumptions for normality and other assumptions for correlation are met, we can choose Pearson's correlation analysis. Otherwise, we will choose Spearman or Kendall's tau, depending on our data type. And remember, we will talk about that later, but when we talk about correlation or relationship, it doesn't mean causality. So causation, it's totally different from correlation. We shouldn't use them interchangeably. So when we say there is a correlation between two variables, it doesn't necessarily mean that variable A causes variable B or variable B causes variable A, or vice versa. So that's not true. When we measure relationships, we do not measure or evaluate causality here. We just want to see if there is any association or relationship between two variables or more than two variables. And also we will talk about partial and semi-partial correlations. So there are two main concepts in statistics. These are core concepts in statistics. We have inferential statistics and descriptive statistics. So descriptive statistics is very simple. Like we measure or we evaluate frequencies. We evaluate or we calculate mean, median, mode, sum, range. These are descriptive statistics. We are describing our data. That's simple. That's easier to do. But we have inferential statistics. We are trying to infer something from the data we have. If we conduct correlation analysis, if we conduct regression, ANOVA, t-test, uh, Mann-Whitney U-test, Wilcoxon sign rank test, and other statistical testing, we are using inferential statistics uh, to make inferences from our data to more general conditions. So in conclusion, we can say inferential statistics is more complex. So for example, does eye color predict diabetes? That's an inferential statistic. We will use regression, for example, in this case. That's complex, that's complicated, that's complex compared to descriptive statistics. There is another example for descriptive statistics is what is the frequency of diabetes in the sample? So we are just kind of evaluating the frequencies in the sample. That's descriptive statistics. So relationships, correlations, or other statistical procedural analysis are inferential statistics. We are inferring, uh, we are making inference from our data to make general conclusions. So when we say measuring relationships or measuring associations or measuring correlations, we want to see whether as one variable increases, what happens to other variable? Does it increase or decrease, or vice versa? Or it stays the same, which shows there is no relationship between two variables. We can do that. Just we want to see if there is any relationship between two variables. We can do that by calculating the covariance. So in covariance, which is one type of uh, one of the one of the main methods of measuring relationships. In covariance, uh, we look at how much each score deviates from the mean. If both variables deviate from the mean by the same amount, they are likely to be related. So that's the concept of covariance. So before doing correlation analysis, it is better to make a scatter plot. So in a scatter plot, we can see if there is any relationship between two variables. We can see a trend in this graph in scatter plot, and we can just, by looking at it, by eyeballing it, we can see if there is any relationship between two variables. We can see if one variable increases, what happens to other variable. We can easily do that by doing a scatter plot, by looking at a scatter plot of the variables. So let's say here we have an example. So we have 5 participants and we have two variables. And those two variables are continuous variable, which means they are numerical variable. For example, here we have two variables, adverts watched and packet spout. So we have two continuous variables here, and we have 5 participants, and we have mean for each variable and standard deviation for each variable. So in this table, S stands for standard deviation. So this is an example. This is a table we have. So if we kind of graph these two variables, so here on the x-axis we have participants 1, 2, 3, 4, 5. So we have 5 participants, and the blue horizontal line and the green horizontal line are the mean of those two variables. And those dots, we have blue and green dots. Those are the observed data. So the difference between the observed data and the mean is our error. That's our error. So if we want to kind of measure relationship between these two variables, we want to see if there is any relationship or if there is any correlation between adverts watched and the packet spout. We need to do covariance or correlation analysis. So this is a revision of variance. Remember from first module, we talked about variance. So variance tells us how much scores deviate from the mean for a single variable. And it is closely linked to the sum of squares. So here, this is the formula for variance. So it is the sum of the difference between each score from the mean square divided by sample size minus 1. That's a variance. Covariance is very similar to the concept of variance, but it's slightly different from it is slightly different from variance, but this is a revision of variance. So remember, variance tells us how much scores deviate from the mean for a single variable. That's the concept of variance. And the formula for variance is like this. So we can measure variance for each variable we have in this table by just plugging in the scores we have for each variable. And then we need to sum the difference between each score from the mean of that variable and square it and divide it by sample size minus 1. So in this case, we have 5 participants. So the n minus 1 will be 4. 5 minus 1 is 4. So this is how we can calculate variance. In order to calculate covariance, which is kind of an indicator for relationship between two variables, we need to calculate the error. So remember, the error is the difference between observed data, observed score from the mean. That's the difference between observed score and the mean. We need to calculate that error between the mean and each subject's score for the first variable. For example, x is our first variable, which is in our example is adverts watched. And then we need to calculate the error between the mean and their score for the second variable, which is our packet spout. And we need to multiply these error values and then add them all these values together and then divide it by n minus 1 again. So we have 5 participants here, n minus 1 is 4. So this is how we calculate covariance. So if we plug in the values and the scores we have in the table into this formula, it will give us 4.25. That's the covariance between variable x and y. There are some problems with covariance. That's true, we can easily calculate covariance by plugging the scores we have in the formula, but there are some problems here. First of all, covariance highly depends on the units of measurement. So, for example, the covariance of two variables measured in miles might be 4.25. But if the same scores are converted to kilometers, the covariance is 11. So how can we interpret this? Depending on the units of measurement, the covariance varies a lot. How can we interpret this? That's a problem with covariance. So there's a solution to this problem. We can standardize it. So if we divide the neurometer by standard deviation of both variables, we can standardize it. So it is, in this case, it is relatively affected by units of measurement in this case. By standardizing covariance, we have correlation coefficient, which in this case, since we have two continuous variables, in this case, it will be Pearson's correlation coefficient. So what is a correlation? When we say correlation or relationship or association, it is a way of measuring the extent to which two variables are related. It also measures the pattern of responses across variables. So we want to see whether a variable, like let's say variable X increases, what happens to variable Y? Does it increase or decrease or it stays the same? So we can kind of, by looking at that relationship between two variables, we can measure correlation. So correlation analysis is a way of measuring relationships between or among variables. For correlation analysis, all data should come from single population. And we have various tests used for correlation analysis. So when we say correlation analysis, it is a broad term, and we have different statistical procedures to conduct correlation analysis depending on our data type. So if our variables are nominal, we can use Cramer's V, which shows correlation between two variables. If our data is ordinal, we can use Spearman's rank. If our data is interval and ratio, we can use Pearson's correlation. The information we get from correlation analysis is nature or really linear relationship between two variables, and also magnitude or strength of linear relationship. So remember, as we mentioned, if you remember from first module when we talked about the different levels of measurement, we had 4 levels of measurement: nominal, ordinal, interval, and ratio. So interval and the ratio levels of measurement will provide more information. They will provide the best information on the nature of the relationship, whether it is positive relationship or negative relationship. So correlation analysis in general provide 2 pieces of information about our data: the nature or the direction of the linear relationship, whether it is a positive relationship or negative relationship between two variables, as well as the strength or magnitude of the linear relationship. Remember, outcomes of correlation analysis are symmetrical rather than asymmetrical. So symmetrical means that the direction of the linear relationship cannot be determined from the analysis. In other words, one cannot say from the correlation analysis that variable A causes variable B. So this is here we have a key point. Correlation is not causation. And when we say the direction of the relationship, whether it is positive or negative, it means if variable A increases, variable B increases as well. So that's a positive relationship. Or if variable A decreases, variable B also decreases. That's a positive relationship. But in negative relationship, if variable A increases, variable B decreases, and vice versa. That's a negative relationship. So from the correlation analysis, we get two important information: the direction, whether it is a positive or negative relationship, and also the strength or the magnitude of the relationship, whether it's a weak relationship, it's a moderate relationship, or it's a strong relationship or correlation between two variables. In this module and in your assignment, when we talk about correlation, we mean bivariate correlation, which means bivariate means two variables. So we are measuring extent of linear relationship between two variables from a single sample. And to do that, we will do Pearson's correlation coefficient if our assumptions for correlation analysis are met. Otherwise, we will switch over to Spearman's correlation or Kendall's tau correlation, depending on the type of data we have and depending on the assumption. So every statistical analysis uh, has their own assumptions. So we need to check for those assumptions before deciding on which analysis we should conduct or carry out. So for the correlation analysis, for the Pearson's correlation coefficient or Pearson's correlation analysis, these are the assumptions we have. First, the nature of the data of the variable should be either interval or ratio, which means they should be continuous variables like body weight, BMI, blood pressure, cholesterol level, triglyceride level, fasting blood glucose level. Uh, that should be a ratio or interval measure. And other variables also can be continuous variable, not just biometric data. Normal distribution of at least one variable. So one of the variables we are measuring the relationship between should be normally distributed. Independence of observational pairs. So variable A should be independent from variable B. So, for example, we cannot uh, we cannot measure the relationship or correlation between BMI and body weight. Of course, they are related. We cannot do that. They are not independent from each other. And homoscedasticity, and this is our last assumption for correlation. And homoscedasticity means evenly dispersed both above and below regression line, which indicates linear relationship. It reflects equal variance. So homoscedasticity is the homogeneous of variance. We also have this for Pearson's correlation coefficient. So as I mentioned, so the assumptions for uh, correlation, Pearson's correlation, are listed here. And also we have a YouTube video. I would like you to watch that. That's very informative. So in order to measure correlation coefficient, we use lowercase r. R stands for Pearson's correlation coefficient. And as I mentioned, uh, covariance has an inherent problem and issue. And in order to solve that, we need to standardize covariance. In order to standardize covariance, we have to divide covariance by the multiply of the standard deviations of two variables. So let's say we have two continuous variables. Let's say we have body weight and fasting blood glucose levels. These are two continuous variables, X and Y, blood pressure or body weight and fasting blood glucose levels. We can calculate the covariance, and then we need to divide that by standard deviations of those two variables. And that will give us correlation coefficient, or R. R is always between -1 and +1. It's always like that. It shouldn't be less than -1, and it shouldn't be above +1. So that's why we get 0.87 here. 0.87 is a positive relationship. So we can say this is from the table we saw in previous slides. The data is from that table. So here we can say there is a positive relationship. There's a positive and a strong relationship because 0.87 is closer to 1, to +1, which is the maximum correlation coefficient. We can say there's a positive and a strong relationship or correlation between adverts watched and packet spout. So here's another example, and this example is from your textbook. Anxiety and exam performance. We have 103 students, and we measure time spent revising, exam performance, exam anxiety, and gender. Remember, gender is a categorical variable, is a binary variable, is a categorical and binary variable. It has two levels, male and female. But time spent revising in hours, exam performance in percentage, and exam anxiety score out of 100. These three variables are continuous variable, and we can easily measure the correlation or relationship among these three variables. So before conducting correlation analysis, as I said, we have to make sure that assumptions for correlation analysis are met. So we need to check for assumptions. First, we have to check for linearity. In order to do that, we can use scatter plots to see if there is any linear relationship between two variables. We can use QQ plots or PP plots, as well as histograms to check for linearity. Then we have to check for normality. Again, scatter plots, QQ plots, PP plots, and histograms can kind of indicate normality. If assumptions are met, let's say there are no outliers and our variables are interval or ratio, we can go with Pearson correlation. If assumptions are not met and we have outliers in our sample, in our data, and the data type, the variable type are ordinal or nominal, they are not interval or ratio, we can choose other methods, including Bootstrap, Spearman, and Kendall's tau. So this is how we do bivariate correlation in SPSS, and I will show you this. This is the output we get from a correlation analysis in SPSS. So as you can see, we have the variables listed here. We have time spent revising, exam performance, and exam anxiety, and we get Pearson correlation and the p-value, which is significance two-tailed. That's our p-value. So there are some important things to know about the correlation. As I said, it is always between -1 and +1. Correlation coefficient, or rho r, the lowercase r, it is the rho. That should be between -1 and +1. So the value of -1 indicates a perfect negative or inverse correlation or relationship. Value of +1 indicates a perfect positive correlation. Value of 0, absolutely no relationship at all, and it is an effect size. So if the rho or R is ±1, ±0.1, it indicates small effect. If it is ±0.3, it indicates medium effect. And if it is ±0.5, it indicates large effect. And also we have rho squared. By squaring the value of rho, you get the proportional variance in one variable shared by the other variable. So here we have three graphs. On the right side, the rho is 0. So as you can see, there is no correlation between variable y on y-axis and variable x on the x-axis. There is no relationship. We have a straight horizontal line. But on the left side, there are two graphs, and we have two lines, and there is a slope for those two lines, and the rho is 0.5 for the above, and rho is minus 0.5 for the bottom graph. So we can say there is a correlation. There's a relationship between variable y and variable x. So the strength or the magnitude of a linear relationship depends on actual strengths of the relationship in the world. So for example, if I want to measure the relationship between the number of ice cream bought and the number of shark attacks, and let's say I found a correlation or relationship between these two variables, but in the nature they shouldn't be correlated, right? So there is no actual strength of the relationship between those two variables. The magnitude or strength of the linear relationship depends on the use of the correct correlation test. So if assumptions are met, but we use Spearman, or if assumptions are not met and we use Pearson's correlation, I will not get correct results from that analysis. And it depends on how many data points are used. If we have a small sample size, we will have a weaker relationship. If we have a larger sample size, most probably we will get more accurate and more strength relationship or correlation. So if results are weak, let's say the rho value is plus minus 0.1, or there are no significance, there is no significant relationship or correlation between two variables. We should ask these questions. Was the relationship actually weak or non-existent? Was the measurement not precise enough? Was the correct correlation test used? Did a type 2 error occur because of insufficient data, because of having a small sample size? So we need to ask these questions if we get weak relationship or non-significant correlation. So as I mentioned, we have positive and negative. So positive means linear, and negative means inverse relationship. And we also talked about the weak and moderate and strong effect size for a relationship. A small sample with a high rho can be non-significant. This is very important. And with a very large sample, the correlation coefficient can be statistically significant when the degree of association is too small to be clinically significant. Therefore, when judging the significance of the coefficient, rho, Pearson's correlation coefficient or rho, we must consider both the size of the coefficient and the significance of the t-test. As I said, correlation is not causation. In any correlation analysis, in any analysis measuring relationship or association, causality between two variables cannot be assumed because there may be other measured or unmeasured variables affecting the results. For the non-parametric correlation analysis, so Pearson's correlation analysis is parametric analysis, and we have two main types of non-parametric correlation analysis. So we have Spearman's rho and Kendall's tau. For the Spearman's rho, we are ranking the data. Let's say our data is ordinal or the assumptions are not met for the Pearson's correlation. We can use Spearman's rho. For the Kendall's tau, whenever our both variables are ordinal, we should use Kendall's tau. And it is better than Spearman's rho for small samples. If you look at like different articles and studies, especially in APA format, most of the time they report correlation matrix. And we will see that in next slide. In correlation matrix, the rho value and the p-value are given for each pair of variables. So it's here. So this is a correlation matrix. And we have variables in columns and the same variables in rows. And we have Pearson correlation, sample size, and the significance level, which is our p-value. So as you can see, we have a value of 1 for marital status in column in the first cell and marital status, because these are the same variables. So of course there's a strong and perfect positive relationship between the same variable, between a variable and itself. So that's why if you look at like the look at a diagonal line, we have 1, 1, 1, 1, because we are looking at the correlation between a variable and itself. Of course, there is a perfect correlation. So that's the APA format correlation matrix. And we can see this in different articles. But let's look at the second cell in the first column. So we have marital status and school level completed. It's minus 0.194, and we have two asterisks, and there is a note below the table. It shows two asterisks means or indicates correlation is significant at the 0.01 level or p-value. So we can just look at this. And remember, we don't need every cell in this matrix. For example, we just look at the relationship between marital status and school level completed. Look at the second cell in first row. That's the same information, because we are looking at school level completed and marital status. or vice versa. Of course, the relationship or correlation would be the same. So in this correlation matrix, we just need a few cells we need to look at. So as I said in the note for the table for the correlation matrix table, there's a note indicates like two asterisks. Correlation is significant at the 0.01 level, which indicates our p-value. This is a correlation output for Spearman's rho, which is kind of similar to Pearson's correlation. Um, So we get confidence interval here, significance, which is our p-value, and Spearman's rho. And this is the Kendall's tau, which is again similar to what we have in Pearson's correlation. And again, confidence intervals. We have partial correlation and semi-partial correlation. So in partial correlation, is here. So in partial correlation, we are looking at the effects of a third variable. So for example, here we have exam and anxiety. That's our two main variables. And like variable X is exam score, and variable B or Y is our anxiety level. That's our two variables, and we are interested in the relationship between these two variables. But there's a third variable, it's called revision. If we measure the correlation between revision and each of the main variables, that's called partial correlation. But in semi-partial, we are just looking at the relationship between a third variable with one of the main variables. That's called semi-partial correlation. For this class, we don't need to worry about partial correlation and semi-partial correlation. We will just use bivariate correlation analysis. And this is how we can do partial correlation. And this is the output for partial correlation. How to report correlation coefficient. So this table shows how to report that. So as I said, this is a correlation matrix. It's called correlation matrix. And in the diagonal line, again, we have 1, 1, 1, which means we are measuring the relationship or correlation between two variables, which are the same variable. So look at this. Exam performance and exam performance, the value of Pearson or rho is 1, which means perfect positive relationship, because we are looking at the correlation between exam performance and itself. So we don't care about that diagonal line. We just care about exam performance and exam anxiety, exam performance and revision time, and also exam anxiety and revision time. So in this matrix, we are looking at just 3 cells. So it says, for example, exam performance and exam anxiety. These are two continuous variables, and we are interested in measuring correlation or relationship between these two variables. So we can use Pearson's correlation coefficient if our assumptions are met. So let's assume our assumption of linearity and normality are met, then there is no outlier in our data. So we can use Pearson's correlation. The rho value here is minus 0.44, and we have 3 asterisks, which means the significance level is less than 0.001, which we have here in the note for that table. And inside the the brackets, we have confidence interval, 95% confidence interval. So by looking at this matrix, I can say there is a correlation between exam performance and exam anxiety. We have also three asterisks for exam performance and revision time, exam anxiety, and revision time. So I would say there is a positive correlation between exam performance and revision time because the raw value is plus. It's not minus. But there is an inverse correlation between exam anxiety and revision time because we have minus 0.71. Sometimes when we measure correlation, the nature of that correlation doesn't make sense because it's not logical. So here in this table, we have correlation with hair color. Is there any correlation between waist circumference or BMI with hair color? And if we look at the p-value, some of them are significant, right? But it is not logical. So we cannot just, measure relationship between any two variables. There should be a logical relationship or logical association between two variables. So here's a summary. So correlation is one of the most common forms of data analysis because it underlies many other analysis. You need to pay attention to the value and sign of rho, which is between -1 and +1, the p-value and the sample size of the data. Here is your assignment. So you will use the data file called FACS 6350 module 5 data file to run correlation on the below variables. So money spent on carryout and BMI at baseline, BMI at baseline and minutes sedentary activity, total cholesterol at baseline and blood pressure at baseline. So you will have 1, 2, 3, 4, 5 variables here, and you should put all these 5 variables in your correlation analysis box at once so that you get one big correlation matrix. And you will need to write these results in APA format, and you will need to report this assignment in your write-up example. We signed module 3. So for this assignment, remember to run descriptive statistics using the variables we have in the data, including the frequencies for gender, race, education level, as well as mean, standard deviation, mean, and maximum for the outcomes of interest. You can also check for normality assumption here by checking the boxes for skewness and kurtosis. Before running correlation, use scatter plot to visualize your data and check for linearity assumption. Remember to put all variables in the variable box and run Pearson's correlation. Please refer to the paper in the next slide for how to write up the results. So here I will show you how to do correlation between BMI at baseline and age. I will go over it with you shortly. And we will interpret the output. So this is how you will write up your results in APA format for correlation. So this is a template. So you can use this. So you will say a Pearson correlation coefficient was calculated to evaluate the relationship between variable 1 and variable 2. There was a significant or non-significant. And you will mention the strengths of relationship, which is either it is weak, medium, or strong and the direction of relationship, whether it's positive or negative, between variable 1 and variable 2, and then you will report the rho, the p-value, that's all. This is in the case where the relationship is significant. If the relationship is not significant, you would say a Pearson correlation coefficient was calculated to evaluate the relationship between variable 1 and variable 2. The results indicated that the relationship between variable 1 and variable 2 was not significant. And then you will report rho and p-value. So here we can say if the relationship or correlation is not significant, there is no need, of course, there is no need to report the direction or the strength of the relationship. So then we will use the values from output, SPSS output, and plug in those values to this template. So for example, I would say a Pearson correlation was conducted to examine the relationship between age and body mass index. Inside the parentheses, the sample size. There was no significant correlation between age and BMI. And then rho inside the parentheses, that's my degree of freedom. And then I will report rho value and then p-value. I can also report 95% confidence interval. So when we report the correlation result, we need to report rho, and inside the parentheses, degree of freedom. So degree of freedom for correlation is sample size minus 2. So my sample size in this example is 319. So degree of freedom should be 317. And then I report the rho value and then p-value. So let me stop here, and I'm gonna show you how to do that in SPSS. All right. So this is our SPSS for module 5 data file. So in order to do correlation analysis, remember you need to do descriptive statistics and like frequencies for some categorical variable, and you will need to report that in results section. But before doing a correlation analysis, I'm gonna build a scatter plot. So here it is chart builder. So I will click on scatter and then click on this. I can drag and drop my variables here. So I'm gonna put age in x-axis and BMI in y-axis, and then click OK. So this is my scatter plot. As I can see from this scatter plot, there is no correlation between two variables. So there is no correlation between age and body mass index at baseline, because you see there is no line here. And if you double click on it, there will be a window popping up, and then here there's an option called add fit line. So I just added a fit line here. It's almost straight and horizontal, and so there is no correlation. But let's assume that there is a correlation. So a scatter plot is normal and there is a correlation. And I wanna run correlation analysis. So I would go to analyze. I would go to correlation bivariate because I have two variables. Even if I have more than two variables, let's say for your assignment, you will have five different variables. You will need to use bivariate correlation again. But in here, you need to just drag and drop all five variables in this variables box and run the analysis. It will give you a correlation matrix. So here I have body mass index at baseline, and age. So I put it here. Make sure that this Pearson box is checked. This is two-tailed. You can click on options and click on means and standard deviation. So it will provide means and standard deviations for each variable I have in the variables list. And then that's all. And also you can click on confidence interval in order to get 95% confidence interval, and then click continue, click OK. So this is the output I will get. So I have descriptive statistics, including the mean and the standard deviation for each variable, and in correlation box. Here is again, I have a correlation matrix here, but the thing is only one cell is important to me. Only the correlation between body mass index and age, because this is a repetitive, right? This is age and age, or age and body mass index, or body mass index and age. So I need to just look at just one cell. So Pearson correlation is minus 0.058, and the significance level or p-value is 0.301. So there is a no significant relationship between age and body mass index at baseline here. And at the bottom, I have another table indicating and showing the 95% confidence interval for my Pearson correlation. So let me create a big correlation matrix so you can see what I mean. So let's say I have age, body mass index, I have total cholesterol at 1 year, systolic blood pressure at 2 year. Let's see what else we have. Money spent on carry out, for example. No, let's remove that. You will do that. So let's say what others. Let's say that's all. I have 4 variables. And again, make sure the means and standard deviations box is checked. You can also check this box to get 95% confidence interval, and then make sure that the Pearson correlation box is checked. So if I had like ordinal level variables, then I would check the Kendall's tau box. Or let's say the assumptions are not met, so my variables are not normally distributed, I would check the Spearman box and then click OK. So here, the first table is descriptive statistics showing mean and standard deviation. The second table is my correlation matrix. This is what you will get. There's a diagonal line just indicating, like, showing 1, 1, 1, 1. I don't care about that. The only thing I care is the correlation between two variables one by one. So even though we call this bivariate correlation, which means two variables, but we have a correlation matrix. So I don't care about let's say, age and total cholesterol. So I don't need to look at that. I'm interested in the correlation between age and systolic blood pressure. So I can just find that. So it says age it's in second row, and then I can find systolic pressure in the last column, and that shows my correlation. And it has 2 asterisks, which means it is significant at 0.01. Let's say there is other thing I need to show you here. And for assumption checking, again, you can use scatter plot or QQ plot or histograms to check for linearity assumption. And you can also check for normality assumption by checking the kurtosis and skewness for each continuous variable to see whether you can run Pearson correlation or you need to switch over to Spearman or Kendall's tau. So I'm pretty sure that these variables are continuous and ratio. I'm pretty sure about that. So I don't need to check whether these are ordinal or nominal, because I know like total cholesterol or age or body mass index are continuous variable. Body mass index can be categorical variable if we categorize it by the BMI cutoff points, but here in this data, this is not categorical. We don't have BMI cutoff points in this data file. So I'm pretty sure that these variables are continuous, they are interval or ratio level. So I'm sure about that. But for the assumption, I need to check for normality. Remember, for Pearson correlation, the one of the variables should be normally distributed, not both. So just at least one of the continuous variables should be normally distributed in order to run Pearson's correlation coefficient. Otherwise, we need to switch over to Spearman's rule. If our two variables are ordinal and if we have a small sample size, we can use Kendall's tau Spearman, and we can choose that here. I want to show you one more thing. So there's an icon here. If you click on that, it will show you what was the analysis you ran recently. So I ran bivariate correlation. So instead of going to analyze and then correlate and bivariate, I can just click on this and it will show me the most recent used analysis. So I can click on that and I can check this box and uncheck Pearson. Let's say these are ordinal variables, or not all, not like none of them are normally distributed. I can check this one or check experiment and run that analysis.